ventilation, external respiration, transport, which is what we are going to start with today. Internal is pretty easy. Cellular is pretty easy too. And I'll just leave the redundancy, just repeating things over and over so they get into your head, but then also we can circle this so that we know we're doing transport. There's 3 parts of transport. We're going to do O2 and CO2. Hemoglobin's so awesome. Hemoglobin loading. We're going to do hemoglobin, which we'll abbreviate now as B. Like oxygen less. And when hemoglobin likes oxygen less, and hemoglobin drops off. I suppose I don't have these numbers. Well, yeah, you kind of won't get them, I guess. That about 2% of your oxygen in your blood right now is dissolved. And a new paper, a big paper. And about 98% is on hemoglobin, so you're highly dependent on hemoglobin. Kind of covered this. Kind of covered this over here. It's CO2. Likes to go into solution better, so it's different for CO2. So for CO2, it's about 7%. Down there, 23%. Yeah, never mind, 23% is dissolved. Sorry, I probably should have said cleared on hemoglobin, or just could have said on hemoglobin. We kind of talked about this before. A problem with, and we're going to write it again, just because redundancy is good. We talked about this before, that CO2 can become acid. The other thing CO2 can do is it can take oxygen off of hemoglobin. And so you don't really carry CO2 on hemoglobin, not a lot. 70% of CO2 is carbonic acid. We're going to do this a lot. The one chemical equation you really have to know in anything, because this is also how the respiratory system controls acid. We'll do that when we get to acid base. Probably heard of bicarbonate. Bicarbonate is your body's base. And again, I'm just going to write it again. You care about this because CO2 is going to equal acid. So take a goes out. But also, this acid is going to also equal potassium and calcium. So you can see that you just can't mess with CO2 because you can't mess with acid. Because if you mess with acid, you mess with potassium, you mess with calcium. Again, you're going to do it up here, and the reason you can't mess with potassium is it's going to throw off your acid. I also like to take my time and draw a graph here. And what we're going to draw is this is going to be oxygen on hemoglobin. You don't really need to use colors, but I just highlight these colors. Hemoglobin has 4 parts. I'm going to draw a squiggly protein here. So this is going to be hemoglobin. It's too small on the screen. So these are, we're going to draw 5 of these. So we're pretending these little squiggles are the proteins that make up hemoglobin. And then we're going to come back and say each one of those will carry out oxygen. So we're going to make the first one not have any oxygen, and then this one's going to have 1 oxygen. This one's going to have 2 oxygen. This one's going to have 3 oxygen. And this one's going to be called saturated. It's called saturated. These down here are called partially saturated. This one is called unsaturated or deoxyhemoglobin. The reason we want to draw this graph is because we have 2 levels of oxygen down here. 2 levels of oxygen down here. So this is going to be oxygen down here. And we're going to go mercury. And so there's 2 levels that we care about. We care about 40 millimeters of mercury, because that's how often it's constituted. That says tissue. And we also care about 100 millimeters of mercury, because that's the level of oxygen in the lung. And put a dot right here. Put a dot, so it's going to come over from here. So it's going to go down to this one. Just put a dot right there. And put another dot. With these 2 connect. And so if we draw it in hemoglobin loading as a curve, kind of like that. What it also means 3/2 on hemoglobin here. And it's 4/2 on hemoglobin. Three oxygen on hemoglobin at the level of oxygen concentration in the tissue, and there's 4 in the lungs. And so what that means is hemoglobin leaves lungs with 4 oxygen and comes back with 3. It seems like a waste. You never like fill up 4 buckets of water, go and feed the cows or water the cows or water the animals by dumping out one bucket of water and returning with three. That would not be very efficient. But it does create a huge buffer. So that means that if you have a low oxygen situation and you keep pumping the blood, there's going to still be oxygen on that ring. And so what this means, this is why CPR works. It keeps flowing. Let it start to clot. It will keep delivering. That's why um, also why this oxygen, the pulse ox is really red laser thing that you put on the finger. Pulse ox, the 95 tells you that you do have a lung problem. So I have a pulse ox just because I want to make sure that my lungs are getting enough oxygen. So this creates a large buffer of oxygen carrying. So you can add a lot more oxygen. And then on top of that, you have another buffer too. Another buffer is your normal breathing. If you take a normal breath out, you still have 3 liters of oxygen in your, or 3 liters of gas in your lungs. And so you always have plenty of extra oxygen just sitting in your lungs, waiting to be loaded on hemoglobin. One last buffer is they say, it's been estimated that the blood only has to go 1/3 of the way through the lungs before it gets filled up. So your lungs are really, really good at filling up with oxygen. It's also why those little canned oxygen things, and I don't know if you don't see as much in sports anymore. You guys ever use oxygen? So like you used to see the football players would breathe in oxygen on the sidelines. They don't do it so much anymore because your lungs are already so good at picking up oxygen. So now we're going to come here to when does hemoglobin drop off oxygen? So we're going to make kind of some sweeping loops. And so keep some space over here. Just come over to this side a little bit. Okay, so I'm going to switch to back. When tissue does work, I mean, you literally release energy and heat when you burn ATP. That's why we call it burning ATP. So when a tissue is using ATP, it's going to increase temperature. It's going to increase it locally in that area. So imagine, well, if you were lifting weights in your bicep, then your biceps is going to be burning ATP, and so it's going to heat up. And so this is going to so increased temperature makes hemoglobin like oxygen less. I suppose the technical way we would say that is it has a decreased affinity. And so that means hemoglobin drops off. tissue that's doing work. And so if you're in a gym and you're working your biceps, or of course if she's playing volleyball and she's jumping out a lot, then her legs are going to use a lot of ATP. As blood goes through there, it's warmer because she's been burning ATP. The hemoglobin's going to like oxygen less. So the hemoglobin's going to deliver the oxygen to where it's needed. Another thing is something called BPG. Sometimes it's called DPG because B, bi, and di will be two. But the only thing you need to know is an increase in BPG is an ATP metabolite. So when you're burning ATP, you make this bisphenol glutamate, and that also is a breakdown product from doing work. So then you're going to bring it. Another one here is going to be acid. So when you feel that burn in your muscle, that's lactic acid, that's acid. And acid also kicks oxygen off of hemoglobin. And then probably even the most important one is increased CO2. Because O2 and CO2 compete for hemoglobin, so they fight over it. And oxygen's higher in lungs, and CO2 is higher in tissue. And this one's so important that it has a name. It's called the Haldane effect. So this is why you also can't have CO2 too high, and why it's carried on carbonic acid. So then you don't have a CO2 kicking oxygen off of hemoglobin where you don't want to kick off. So when you breathe in air, you have oxygen in your lungs. It's higher in your lungs. Therefore, oxygen kicks CO2 off of hemoglobin and you breathe it out. When you deliver that hemoglobin to the tissue and CO2 is higher, when CO2 is higher, it kicks oxygen off, and so that oxygen then is being delivered to the tissue. And again, just always wanting to be redundant. I'm going to go ahead and we'll put 4 down here and we'll call it the anemia. And there's some things that I just really think you should absolutely memorize. One is the anemias. Other things are like what hematocrit is. Remember that there are 3 main cases: low RBCs, low hemoglobin, and bad hemoglobin. Let's do the easy ones first. This one's sickle cell. This one's the other way that hemoglobin will go bad. It's called thalassemia. Low hemoglobin can be iron deficiency, or it can also be B12 deficiency, which is called pernicious. The thing with B12 is, I'm going to say it again, I'm going to keep saying this, is that you need the B12 to make methionine. You need methionine because it's the first amino acid in every protein you make. So if you don't have B12, you can't make protein, and if you can't make protein, you can't make hemoglobin, and so you won't have enough hemoglobin. So it's one of those things that's really important. Like the one cool thing about it's probably the first time, other than like old-fashioned diseases, but this COVID virus, it's the first time when taking vitamin D and probably taking your vitamin B is definitely preventing or at least lessening the symptoms. So it's one of the first times where we're seeing a disease associated with vitamin usage, and not just malnutrition, but having a regular amount of vitamin is protective against the disease. I mean, that doesn't happen real often. I mean, you get a little bit of rickets and sometimes a little bit of I don't know, rickets. Tired. Osteomalacia is what it's called. That's when you get weakened bones. You can have two little red blood cells by having hemorrhagic. So this is hemorrhagic anemia, and this is blood bleeding. You can have aplastic, which is a problem with your bone marrow. And then you can have hemolytic. And that's when blood cells die. So you should know your needs. And hemolytic. And then I'm gonna write this one out quick, and you don't really have to know it, so that I think it's good. It's one of those things where pain cause hyperventilation. So if you're in a lot of pain, it has to be treated. I mean, it's really kind of interesting to look at how pain is being managed these days. You have to manage pain because it can lead to a lot of problems, because pain leads to hyperventilation, and that leads to low CO2, and that means you're going to get less O2 to brain, and that means you get altered mental function. Keep in mind that low CO2 is going to do a bunch of things, like it's going to decrease acid, that's going to decrease oxygen drop off. So acid causes hemoglobin to drop off oxygen. This here alone too, less CO2, taking the O2 off hemoglobin. So here again, we're doing that. Also, less CO2 causes vasoconstriction. So we've talked about this in a lot of different ways. We talked about it as in the gym and you're working your biceps and you have low oxygen, then you'll increase flow. But if you have high oxygen and low CO2, then that'll lead to vasoconstriction. And then also, this CO2, this acid, is going to cause low potassium, it's going to cause low calcium. And so that's going to alter action potentials, could alter action potentials in the lungs. So all of these together are going to cause people to start acting weird. And you don't know how they're going to act. It's kind of like how alcohol, you never know how it's going to affect somebody, if it makes them really nice or if it makes them really mean. Pain can cause a lot of different changes in function. You don't know how it's going to change it. Okay, so I always like to point that one out to the dental hygienist, that you can't let somebody experience a lot of pain because it can really affect how they act. Okay, so I'm going to come back here and draw this out really fast. Ventilation. external. Transport. Internal respiration. And cellular. And these are smaller, so we can do these both on one page. So do this on page. Do this on page. And I probably draw this out more than I have to, but I've just seen that students get this confused. So that's supposed to be a lung. Then this should be capillary. So we're going to call this tissue. And O2 is going to go here, through here, and here. And this is, we've already done this one, but again, students just get it confused sometimes because they think external means breathing out and internal means breathing in, but this is external. So from the lungs into the blood is external. And this is internal. So we're only drawing external just to show that it's different. And then CO2 is going to go this way. There's only a few things that affect internal, and that would be like if you had a house fire, increases CO2, then you'll be shoving CO2 towards tissue. We'll talk about this when we get to the next section. I don't know if I mentioned it before, but the DNA system is we'll talk about a house fire when it's shoving CO2 into the tissue. It's also causing acidosis, and that can damage capillaries. It's also going to throw off iron concentrations like potassium and calcium. And so people that are on fires can die of cardiac arrest because the smoke changes their chemistry of their blood. I'm going to do the same color as, try to do the same color as I did capillary. So internal respiration is going to be a problem with capillary. C with a line over it like that, sorry. Use width. And so it can be things like congenital. So you're born with it, congenital lack of capillaries. Some people don't have as many capillaries. Or you can also get rarefaction. Capillaries die. Diabetes. Because the sugar in blood makes it sticky. So we generally probably all know that, sorry, that didn't sound like it. But one of the problems with diabetes mellitus is lack of circulation, and sometimes it can lose limbs because that sugar will clog up their capillaries. Kind of like I always think about it is if you spill pop on a counter and it's not diet pop, and you fail to wipe it up, then it'll get really, really sticky. And then the last one is going to be sickle cell. So what happens in sickle cell Vesicled cells. Vesicled cells block capillary. So capillary, I have it on this computer. I'll try real quick. So a lot of times we do research in MP2. We're just not doing it now because it's just not a good time to work in groups. That's another good thing for COVID. No group work. So they took these two little goldfish they bought at Walmart. This is Little Blackie, and then the goldfish is DJ. Little Blackie and DJ lived in my daughter's fish tank for quite some time, even though they're just Walmart fish. So here they put some Red Bull in it, and you see this guy, little DJ, going crazy. He's on the side, and he's kind of flipping out. The cool thing, the reason to do this is because, now this is a really short video, like a second long. If you look up here, you can kind of see where the red blood cells are going single file through a capillary. So some places you can catch it. So what we did is we took the fish and we put its tail under a microscope, and you can actually see blood cells kind of flowing. And the reason I'm showing this to you now is just because, for two reasons. See how much faster, like they're kind of blurry, but you can see just how much faster the red blood cells are running. So don't drink Red Bull. It's not good for your blood cells. But I also just wanted to show the blood cells go through capillaries one at a time. So they're cycled and they can block with capillaries. Okay, hopefully we have plenty of color for this one. I like to do this in kind of color coding. So the first thing I'm going to draw for cellular respiration is a mitochondria. And the whole reason you're breathing in 15 to 18 times a minute is because you're going to take, I don't know, yeah, I'll try and draw it all out. So you're going to take C6, H12, and then use O for this. And this is going to be O6. I'm going to add O2 to this, 6 O2s to this. So 1 C6H12. And what this molecule is right here is glucose. And at the other end of this equation, you're going to get 6 H2O plus 6 CO2 plus 36 ATP. So you're converting all your food, however you make your food, however you eat your food, you're going to convert it into glucose, you're going to add oxygen to it. And technically what you're doing is you're taking a bunch of this oxygen and you're putting the oxygen in here. So these oxygens are going in here. You're also going to take a bunch of hydrogen. You're going to pick these hydrogens off. You're going to put them on the outside of the mitochondria. But then what you're going to do is you're going to let the hydrogen combine with the oxygen You're going to make ATP. You're going to take those oxygens and turn them into water. And you're going to take some of them and attach them to the original carbon from the glucose and breathe it out as CO2. So we're going to talk about this when we get to the urinary system, but you're going to constantly be making acid. And so cellular respiration is going to take these oxygens, attach them to these carbons so that you can make ATP. So then that means that any kind of the key word for cellular respiration are mitochondrial disorders. And I still remember saying it less than 10 years ago. And if you have a mitochondrial problem, you just don't exist, because if you don't make ATP, then you cannot live. Since then that's been proven wrong, because it's really kind of interesting to go back and teach AP1. I don't teach a whole lot of AP1, but we're finally starting to figure out diseases associated with cellular compartments, or cellular parts, like disorders of the lysosome, disorders of the mitochondria. So aging is thought to be a mitochondrial disorder. So it's really kind of cool that your mitochondrial DNA came from your mom. So it's thought that mitochondria originally were bacteria that invaded cells, and then those cells just kind of took them over and used them to make energy. So they have completely separate DNA, and so mitochondria don't have the same ability to repair their DNA that your nuclear DNA does, and so they're more prone to errors. And it's called Eve DNA because technically, if your mom gave you your mitochondrial DNA and her mom gave her mitochondrial DNA, so on and so forth, then it all came back to one female. If I would go to, hopefully we're gonna, by the time you're learn these drawings, you're gonna realize this keyword. Sorry, my mouse doesn't work right here. Right, can't see it. You're gonna go to Wikipedia and you're gonna associate keywords in these drawings. So if you're gonna find a cellular respiration disorder, you're gonna look at mitochondrial disorder. You're gonna find an internal respiration disorder, you're looking for a problem with capillaries. If you're looking for a disorder of transport, you're looking for oxygen, CO2, or probably hemoglobin, or you can also do one of the anemia. For external, you're going to be looking for gases, or you're going to be looking for fluid and mucus for the most part. And then for ventilation, you're going to look for things like mucus, fluid, scar tissue, surfactant, and emphysema. So you're going to look up and find 5 pathologies. And so don't just looking for about the shortest thing would be this one, but find a specific one. Like if I were to ask you, I don't know why I'm picking on you courses today, but if I were to say, what part of your body uses the most? Picking on you, not picking on what system do you think would be affected most if you didn't have enough mitochondria? Who's using the most ATP? Your teammates, just like, normally a teammate would be like, I'm gonna try and help her out a little bit, but she's not. You can just see on her face that she's just leaving behind it completely. She's not willing to help you at all. So your brain, technically, the organ that uses the most CO2 is your kidneys, but your brain is right up there. So I would do like Lay's disease is one that I would like to do. This food is really bugging. Yeah, Lay syndrome. I'm gonna give you some symptoms. So I would expect the symptoms to be problems with mental functioning. So can't do anything. So disorders of the muscular system, disorders of the brain. But that's a good one for like mitochondria. This is a good paragraph that we talked about mitochondria. So that's your essay for this test. Hopefully, like I'm just tired of all good at. I'm pretty sure you are too. This should be a fairly simple test. 25 multiple choice, just over respiratory. 5 respiratory pathologies. Once you have the drawings down, then finding the pathology should really be pretty simple. One warning I'll give you is that if you see fluid or mucus, I definitely want you to show me that you know Boyle's law, because again, it's just one of those things that simple physics helps you break down how something in the alveolus is affecting the whole organism, like how a water molecule or a mucus molecule can affect all other levels of anatomical hierarchy. So I guess I would like to know that too. Any questions? And then 5 digestive. I'm looking for 2 to 3 sentences on digestion, really not looking for much. Ulcers are caused by Helicobacter pylori. It's a bacteria that if you treat it, then the ulcer usually goes away. Echolalia, that one's funny to say. Echolalia is called the cardiac valve in your esophagus that lets food into your stomach. It's achalasia, so it's AC. Achalasia, sometimes it closes, and then you think, well, that's kind of bad because now the food can't get down into my stomach. But the worst part is again, your immune system is ready to deal with problems where it expects it to be, but it does not expect food to be sitting in the esophagus. So actually what happens with achalasia is the food rots in the esophagus, so then that rottenness makes the whole esophagus spoil. So that's what I'm looking for digestion. Any questions? Now I'm like real subconscious about my nose. Really bad news for your lab. And that is, again, I don't know. I've said this multiple times, it's just October. October just and then it's just draining to politics and all that stuff going on. So I forgot your test on the kitchen table. So we were supposed to go over your immune test. But unless y'all want to drive over to the Henniger house where my daughter is being some weird COVID series, then we'll have to do it. I definitely want to show you your immune test because I want to show you where you miss points. But I unfortunately don't have it. Let's see if we got about halfway here.